Welcome to the TransferLab seminar, which is part of the Applied AI Institute for Europe. Our seminar is a platform where researchers and engineers share and discuss recent advances in AI and ML. In today's seminar, Sridhar Chellappa will talk about or will give an introduction to reduced order modeling. Sridhar works as a postdoctoral researcher at the MPI for Dynamical Systems in Magdeburg, Germany. He has a background in applied mathematics and electrical engineering. And with that, I will give the mic to Sridhar. Welcome. Thanks for being here.
Yeah, thanks for the introduction, Jan, and also thanks for the kind invitation to present in this seminar series. It's a great honor, and also I'm quite excited to give you an idea about reduced order modeling, which was my main topic of focus during my PhD and kind of continues to be one of the topics that I'm looking on during my postdoc phase. So let me start actually by giving a very broad overview. As scientists and engineers, we study different phenomena, physical processes around us in order to both understand these phenomena and also, take advantage of these phenomena so that we can benefit the larger humanity or human society. You can think of a number of different physical processes that are relevant, especially in our modern times. Things like climate science is very important. So there's a need to understand the physical processes underlying climate science. We want, lots of clean and sustainable energy. So things like nuclear fusion and wind farms in a very large scale needs to be considered. And also things like, in the field of biology or medicine, cardiology, for example, which is one of the main causes of human mortality. So there's a need to study these larger physical phenomena and somehow leverage this knowledge to various beneficial ends. So if you look at trying to understanding different physical processes, there's broadly, two approaches that one can take. One is based on modeling the PDE, the partial differential equations, or also known as the physics-based approach. And we also have the data-based approach where there need not be an underlying model, but you still want to, study the phenomena. So let me talk about the physics-based or the PDE-based approach first. Typically, the starting point for this is human observation, human thought. You look at the world around you, you perform experiments, come up with interesting equations, such as the one shown here, relating different physical phenomena. So, for example, you can think of Newton's laws as a classical example of this kind of thought-based or observation-based modeling process. And we have many, many other equations that also come up as a result of this, like the heat equation. Quantum mechanics has the Schrödinger equations, Maxwell's equations, so on and so forth. This is one way to study the nature. And the other end of the spectrum, the data-based approach is especially relevant when, some process that you're trying to model cannot be captured easily. So a very classical example would be the financial or the stock market. To the best that we know today, there is no underlying model that explains, exactly how high the stock price will go tomorrow or how much it will fall. But what people instead adopt is a way to look at the historical data and make predictions based on, correlations between different phenomena in this data. And this also extends to fields like computer vision. So if you have self-driving cars, you don't necessarily have to have the model of the surroundings of the car. Instead, you look at data like coming from sensors, coming from microwave antennas or, cameras. And then all of these data is kind of fused together in order to build the model that the car eventually sees. And such data-based approaches are also relevant to many other fields, such as also in acoustics. So in this talk, I want to briefly touch upon both, reduced order modeling for both kinds of viewpoints. First, let me talk about the PDE-based approaches. So we have known partial differential equations for quite a few centuries, right from the 14th or the 15th century. And people have tried many different approaches to solve these PDEs, starting from just pen and paper, using things like analog computers, giving that up, and eventually, taking over human computers in order to solve the equations. For example, human computers were used during the World War time by many government agencies to, perform calculations. And very recently, in fact, starting from the 70s to the 80s, when the Silicon Revolution really started, PDEs are mainly solved in chips, either in your laptops or, in large supercomputing clusters. Solving PDEs has become more or less routine nowadays because there are many, many standard approaches. You can think of finite difference method, finite element, finite volume method. And the underlying philosophy of all of these standard approaches is the following. So you have some spatial domain where you want to solve your equations. You kind of discretize this domain. In the case of the finite element, you use like some shape functions, these triangle shapes. Or in the case of finite difference and finite volume, you basically use some kind of grids, which can either be regular or irregular grids. and the equations are solved for each of these nodes. So more or less, the approaches are well studied, well established. Nevertheless, there are many challenges when it comes to solving these equations. First thing, beyond the most simple partial differential equation, there are no known analytical solutions for most of these. Therefore, we have to only consider numerical approaches. And the challenges that we face when solving these are, of course, nature is nonlinear. Therefore, the equations are also nonlinear. And very often you find the PD variables are coupled very tightly, and therefore solving them is not so straightforward. And all this discretization leads to very high dimensional systems where, once again, the computational cost can explode. In terms of applications where PDs find use, of course, there are numerous applications. A classical example would be design optimization, where a company is trying to come up with a new product, let's say a new car. They have to start from the prototype, build some models, build a computer model, iterate through different parameters like what materials to use, the thickness of some particular material that you want to use in the car, the shape of the car, so on and so forth. So all of these means that your computer model gets solved millions of times in order to get to the final result. This is exactly the challenge that we want to address, meaning solving these equations, especially high resolution equations, in a multi-query setting like design optimization or in real-time simulations. For example, in control, if you want to embed your model within a controller, then the controller needs to solve the model in real time. So all these are challenging situations. And that kind of motivates the need for reduced order modeling, why we need reduced order models for enabling such fast simulations. So that's like a broad overview that I wanted to present. But let's now move on and go into a little bit the specifics. So what exactly we are trying to solve, what's the setup and so on. Once you discretize your system of equations, you're going to end up with this set of ordinary differential equations. I'm going to call this the full order model, meaning this is your true high fidelity model that you can have of the equations. U is going to be the variable that you want to solve for. In the discrete setting, this is going to be a vector of dimension capital N. And it potentially depends on time. So meaning we have a dynamical system. And also this mu, which could be different system parameters. For example, if you think of a fluid, this could be the viscosity of the fluid. So the solution changes depends on what some material parameter of the fluid or some other processes. E and A are matrices of dimension n by n, which come from discretizing your different partial differential parts like diffusion part or a convection part, so on and so forth. In the setting of finite elements, this would be called a mass matrix, and this A is usually known as a stiffness matrix. The nonlinear paths we discretize in the form of this vector F, which is also of dimension capital N. And typically in many applications, you want to excite your system with inputs or some perturbations. And those can be modeled by the input signal S, which depends on time t, and this input matrix P. Also, you want to start your system with some initial condition. The configuration is represented by U0. That's the overall setup for the full order model. Now, to just go into a little bit specifics of the computational costs of doing this. You discretize this equation, and then if you want to do one linear solve, it's going to scale as order n to the x. So n is, of course, the dimension of the full order model. And x typically is a factor between 1 and 3, depending on whether you have something called as a dense system or sparse system, meaning if your matrices E and A are mostly empty, mostly zeros, then the cost is less. Of course, you want to simulate it for some specific instances of time. Let's call it nt. And because the system is nonlinear, you want to be able to do a few Newton iterations. So that also goes in front of this cost. So if your n happens to be large, which is typically the case when you discretize partial differential equations, you can think of n as being in the orders of tens of thousands. And in many applications, it often tends to be in the millions. Then the cost of solving for just one parameter configuration is quite expensive already. And if you want to do on top of this for different inputs S, which is typically the case, and also for different parameters, then you can imagine that all of this becomes quite expensive and you need very specialized hardware, for example, clusters to run your simulations. So therefore, we want to come up with a surrogate model or a reduced order model. So the reduced order essentially means the following. So order refers to the number of equations here. So we have n equations and we want to reduce the order to something smaller. And the first step to do that is, of course, to make an approximation. So I'm going to, for the purpose of today's talk, I will just talk about linear reduced order models, meaning approximations in the form shown here, where I write my original U as V times U hat. So V is something like a projection matrix or a basis matrix. and U hat are the reduced coefficients now of small dimension small n. So I take this approximation and then directly plug this onto the equation here. And this gives me the first equation shown here. All I've done is just taken this and plugged it directly onto U. This equation is an overdetermined system, meaning we have capital N equations, but we only have small n unknowns. In order to make the system square again, we do the next step, which is projection using a different matrix, W. And in the literature, this is technically referred to as a Petrov-Galerkin projection. So the first step is the approximation using the V. And the second step is the projection using the W. And once I do this, I just have to multiply the matrix inside and then set this whole expression to 0. Now, just to mention here, the dimension of the projection matrix W is also the same as V. So n times n. All right, so let's take this expression now, and then we just multiply the W's inside, and this gives us the reduced order model. So all the quantities with the hat now are of smaller dimension, so meaning they are small n by small n matrices. We have reduced the number of equations from capital N to small n, and that's hopefully going to give us a lot of speed up. And we do the same with the nonlinearity and also the input matrix P. So one key assumption that we need in order to write an expression like this is the following. We assume that the matrices, for example, E, follow what is called as a affine parameter dependence. What this means is very simple. I assume that, I can write this E of mu matrix, for example, in the sum of products form. So the product has two factors, theta and E. And the key assumption is that all the dependency on the parameter comes on the first part of this expression. And these factors EIR essentially can be written independent of your parameter. So what this essentially allows you to do is that when you do this projection step, for example, here, you can individually reduce the factors E hat by multiplying with W and V. And this allows you to write the E hat as a sum of products of these E hat factors now. What we have essentially done in the background is that we've gone from something that required order capital N operations, because these are multiplications with n by n matrices. Instead, we've gone from that to just a summation of small n by small n dimension matrices. So that really gives you the key speed up in order to obtain this reduced order model. Now, I also want to mention here that not all systems follow this affine parameter dependence. Some systems, you cannot write the matrix in this form. And for that, there are some specialized techniques that one can use in order to recover this kind of a formulation. I will briefly talk about this in one of the next slides. Assuming that this assumption holds good for this model, then this is the computational cost. So we have the same number of time steps and number of Newton steps. And now the cost of solving one linear solve of this model is just n to the x, small n to the power x, with the resulting speed up of capital N by small n. Now, if, as I said, n tends to be quite large, let's say you have like a 10,000 dimension system, you can potentially expect it to reduce quite a bit, assuming that, then let's say order 10. And this already gives you quite a bit of speed up, a factor 100 or even 1,000 times speed up compared to solving the full order model. And hopefully, I've convinced that you can simulate the reduced order model much faster than solving the full order model. Just to also mention here that different projection-based reduced order modeling approaches largely distinguish themselves in how they compute the V and the W. So the V and the W are the key in order to get a good reduced order model. And that's essentially the main formulations of your projection-based reduced order models. Let's move ahead. I'm going to use this example of a Burgers equation as kind of a running example throughout this talk to kind of illustrate the relative merits and demerits of the different method that I will talk about. So this is just a 1D partial differential equation in the spatial domain 0 to 1 and time 0 to 2. So here are two examples of the snapshots of these. So the parameter that I want to vary is going to be the mu, which is the viscosity of the Burgers equation. And I will vary this in this range from 10 to the minus 3 to 1. I discretize this equation by hand using finite volume method to give me some system of dimension 1000, which I can write in the form of my full order model. And it looks exactly like this. I mentioned that I discretize this using finite volume method, but this is not a limitation because you can use potentially any available software package. For example, you can look at Phoenix, which is a finite element-based library, and then you can, formulate the spatial domain, write out your weak forms, so on and so forth. And then you can actually extract these E and A and B matrices out of Phoenix just by making some function calls. So you can do this a fairly straightforward manner, at least for, small examples. Right. So I will use this example throughout to illustrate different aspects that I want to highlight. Now let's look at different reduced order model methods. So Broadly speaking, you can classify them in these three categories. This is not a very strict classification. There are, of course, overlaps, but roughly speaking, you can, classify them as physics or projection-based reduced order models, data-driven methods, and also hybrid methods. Within these projection-based approaches, of course, there's a well-known proper orthogonal decomposition, which has been around right from the 80s almost. Then there is the reduced basis method, which is like a smarter way of doing the POD, which has been in development right from the early 2000s. There are these methods from the system theory or control theory community, like balance truncation, moment matching, that is often quite widely used in the electronics communities as well. Then we have the data-driven methods. As you can see from the years here, these are fairly more recent. Thanks to the ML revolution, there's been an explosion of many data-driven methods. Operator inference, POD-NN, just POD with a neural network, deep learning-based reduced order models, the very famous dynamic mode decomposition, SIMD algorithms, and of course, more recently, things like DeepONet neural operators. Hybrid methods are those methods that kind of make use of both data-driven and physics in some manner. The classic example of this is, of course, the physics-informed neural networks, or PINs, where it is a data-driven approach which tries to learn some mappings, but the physics comes in the form of the loss function, where the PD residual basically goes into your loss function, and that takes care of the physics. So that's why I call this a hybrid approach. In the next 15-20 minutes, I will just try to focus on these 4 or 5 main methods. So 2 from the projection approach, and then 2 or 3 from this data-driven methods. Throughout this talk, I will also try to argue that you can put most of the methods that I showed in the previous slide in this very general structure. So you start with your high-dimensional solution, U. You do some form of an encoding, which I will specify for each method. You do the encoding and you go into the latent space, and some magic happens in the latent space. And then following that, you can decode the latent vectors and then reconstruct your U tilde. So basically, I will just try to illustrate for each method how you can put them in this very general form that is shown in the picture here. So let's look at the POD method, which yes, many of us know here. It's a very, very simple method. So just to have a broad idea, let's look at each of the steps of the POD. So the starting point is of course, data. So we collect data by solving the ordinary differential equation, the full order model, at a bunch of parameter samples denoted by mu, at n mu samples to be specific. And we collect snapshots. So these vectors are essentially the solution u at different time, t, and at different parameters, mu, which gives us this big matrix of dimension shown here. Once you collect the data and put this in the snapshot matrix, of course, then the next step is to do the POD. In practice, this can be realized by a singular value decomposition. So in Python, it's just a matter of importing scipy.lean_alg and then importing the SVD function there. Then we call the SVD on the snapshot matrix, and the result gives us 3 factors. So the L and the Q are the so-called left and the right singular vectors, and the sigma are the singular values. So the interpretation, at least in an intuitive sense, is that what we're doing is essentially some form of generalized eigenvalue decomposition, with L and Q denoting some eigenvectors or singular vectors, and the singular value sigma standing for products of eigenvalues. So there's a nice physical interpretation to POD. And then you pick out your projection matrix V in the following way. You just set the first small n columns of the left singular vectors L, and then set that to be a V. Typically in the POD, we set also the other projection matrix that we had W to be the same. Then once we have V and W, it's just a matter of projecting and then obtaining your reduced matrices E hat, A hat, and so on. Right, so that looks all very nice and easy. Let's look at the advantage and disadvantages of these things. The implementation is quite simple. As you see, it's just a matter of 3 algorithmic steps. And of course, there is a nice interpretation in terms of the eigen decomposition. And also, you can think of as projection of your equations onto a reduced dimension space denoted by V. So as a drawbacks, we need lots and lots of data. If you want to cover enough dynamics that you want to approximate, then n mu should be large. And of course, the choice of the small n, where you truncate the left singular vectors, is somehow heuristic. And as a corollary of that, there is no accuracy guarantee, meaning if I say that, I choose 10 basis vectors, I don't get an error of some tolerance, let's say 1% or 5%. So there is no clear way to bound the error of the POD approximation based on how many left singular vectors you choose. So that's one of the disadvantages of POD. As I mentioned, let me illustrate the POD using the Burgers equation toy example. So very nice and simple. I just pick 50 samples from the training set for training and 50 from the forms the test set. So I collect these 50 snapshot data, and then I perform the singular value decomposition. And the first step that I want to do is determine my n. So how many columns of the left singular vectors that you want to have. So based on the tolerance, I simply plot the elements of the singular values. And then I say the first index, which goes below 10 power minus 4, is going to be my reduced dimension 11. So then I pick 11 singular vectors, and this is going to be my projection basis. Training time, which means the time for the collection of the data, and also the SVD is about 31 seconds for this toy example. The inference time is very, very fast, 0.02 seconds. And when we compare the speed with the full order model solve, you get around 15 times speed up. So this works very nice for the Burgers equation at least. And the test error that you get is around 1 to 2% error on the test set. And here is an example of the test parameter performance at 0.005 and 0.003 respectively. Okay, so that seems Burgers at least works with POD, but of course there are some challenges. I just want to briefly mention now how you can put this POD ROM in the unified structure that I mentioned before. So the encoding step, remember we had the encoding. Now that is replaced by the projection. So we simply have V transpose as the encoder, and the decoder becomes the unprojection or the multiplication with V. And the magic happens in the latent space in the form of the latent ODE. So because we have the model, we can project and get the latent ODE, and then we can propagate forward the ODE by solving it. And then for each time instances, you can just apply the decoder and then obtain the corresponding decoded version of your approximation. Let's talk about some other challenge that arises with the POD reduced order model. So this was the reduced order model that we obtained from the POD. And I want to especially focus on how we evaluate the nonlinear part f hat. Now, the f hat is of dimension r to the small n, so it's a small n dimension vector. But if you pay close attention to the computation here, you actually need to perform operations that scale with the full dimension if you want to evaluate this vector. Why is that? Well, the thing is you have to multiply v times u hat, which is already giving you a dimension capital N vector. And you want to evaluate the function at each of those endpoints. So the cost, as you can see, scales with the full dimension, which we do not want at all, because we want that the reduced order model is somehow independent of the dimension capital N, which can be quite large. Therefore, the idea is to come up with a clever technique to somehow reconstruct f hat by only using a few evaluations denoted by L of the function f instead of using the full function. This is the motivation. Many clever people took inspiration from what was happening in the 90s in the image reconstruction community, where the idea of GAPI reconstruction or GAPI POD was already proposed in 1995. So the problem that the image people were trying to solve is the following. So you have some underlying truth image, but all you have is pixelated or masked pixelated data of the original image. So the question was how you can go from this masked data back to this true data. So how you can reconstruct the image. And for this, the idea that they came up with was to basically use a concept called eigenfaces. So the idea was that you trained by collecting a lot of image data, and then you performed an eigenvalue decomposition and extract the eigenmodes. And then the algorithm involved like a clever combination of this masked data and the existing library of eigenfaces to come up with a reconstruction of this. So that was the method from the image community. And that was borrowed onto the literature of dynamical systems in order to address, for example, the challenge of evaluating f hat. So these family of methods go by the name of hyperreduction within the reduced order modeling community. The specific method that I want to briefly talk about is the DEIM or DIME method, which was introduced back in 2010. So the idea is essentially the same what was used for images. You only want to evaluate your true function f at only a small number of points shown by this diamond, and then using some clever tricks to basically write the approximation in an efficient way. The idea is the following. You have to collect snapshots, once again, of the nonlinear function now, denoted by f of v times u hat. You collected data at many time and parameter instances and then perform a POD, and then you get this basis vector u, which you then basically combine with the partial function evaluation in the form shown here. And the nice thing about this is that you can actually pre-compute all of this. The first factor can be completely pre-computed and stored during the training stage. And when you want to do the inference of the nonlinear part, all you have to do is sample the function at L locations. Therefore, we already achieve like quite a bit of speed up because L is usually very, very small compared to capital N. So that's the main idea of the DIME method. This has also found a lot of applications, not just in dynamical systems, but even beyond. For example, you can use it to choose sensor locations. So which are the good sensor locations that you want to put in your system to make a pseudo-optimal reconstruction of your field. There are many such related methods also available in the literature. So that's the idea that we will use in order to, improve the POD-ROM. So I illustrate this on the Burgers equation once again. Same setup as before. We had 50 training samples. The ROM dimension is also the same, 11. But now we also have this extra hyperreduction step where I choose 12 basis vectors for the U matrix. If I compare the training times of these two, then I, of course, need a little bit more because the hyperreduction step means that I also have to collect extra data of the nonlinear part and, do the POD. But the key part is the inference time. So even for this very small example, we are already getting like a 50% reduction in the inference cost. And from past experience on more large-scale example, I can tell you that it's absolutely crucial that one has to use hyperreduction if you want to use projection-based reduced order model for nonlinear systems. So that becomes essential in a sense. That was treating the nonlinearity efficiently. But there's also one other issue with the POD, which is the need for data. So you have to sample your parameter space enough to collect the snapshots. And this can be a problem, if it's very hard to compute solutions of your full order model, which can be due to issues of not having enough data or computational resources. And that's where the next reduced order modeling method, the reduced basis method, really comes in. Just in a nutshell, it's a very smart way of doing the POD. And I will just show that in the next slide. In the POD, we just collect data and then, you just apply the singular value decomposition. But in the case of the reduced basis method, we do this in an iterative fashion, which I will just briefly explain now. We start with the pool of parameter samples, mu1 to mu(s). So we don't solve the differential equation for all samples. We just have this parameter set. To begin with, in the first iteration, we solve the full order model at exactly one sample from this, which is denoted by mu star I. And then you collect the snapshots, you perform the POD on the snapshots, you get your projection basis VI. And you can use this VI just like we did before to get your reduced matrices E hat, A hat, and so on, which gives you the reduced order model. Now, the next step is key because in the next step, you choose the next parameter sample where you have to solve your full order model. And how do we do this? Well, we just solve this maximization problem. So the idea is the following. You look at all parameter samples present in your pool, which is this set. And then you look for the parameter that maximizes this quantity delta mu. And then you choose that as your next parameter where you solve your full order model. And the motivation of using the delta mu is the following. So the delta mu is nothing but an error estimator. So it's a way to tell you how close your reduced order model approximation, U tilde, is to the true solution, but in a computationally efficient manner. So you use this error estimator, and then in this way, you iteratively pick samples. So let's say you pick the second sample, and then you solve the full order model of the second sample, and so on, and until you reach some kind of a tolerance which you set for the model. As you can already see, we do not need a lot of data compared to the POD because we are doing the enrichment of the basis V in a step-by-step manner. And this also makes the choice of the reduced dimension N automatic in some sense. And the second and most crucial advantage of the reduced basis method is, of course, error certification. So because we are using this delta mu as a guide to tell us where to sample, and because delta mu is essentially a bound for your true error in the approximation, you more or less ensure that at least for the test parameter samples you use, your reduced order model is always going to have error less than the desired tolerance. And this is a very critical advantage in many applications because you can really believe in your reduced order model. And of course, the price you pay for this is that the implementation now is not so straightforward. So you have this greedy iterative steps, and then you also have to come up with clever error estimators for this to work. So the implementation is, of course, a little bit more involved, and that's the price one has to pay. Just talking a little bit more about this error estimator. So as I mentioned, the error estimator is some kind of a estimate or a bound for the true error at each parameter mu and also time instance t. What can be used for error estimators? The most logical or the easy one that one can think of are the residual-based error estimators. So where I just take my original equations of the full order model and then plug in the approximation U tilde into it. And basically, I can approximate this whole expression using some quadrature for each time instance. Let's say you can just apply quadrature and then compute it for different time instances. While this is easy, this is not the best one can do. There are many sophisticated, mature methods available in the literature Two of the examples are cited here. I also worked on error estimators a little bit during my PhD. You can do a lot of things, theoretical things with this, and then come up with very nice approximations for the true error. And the two desired qualities that we need, of course, for the error estimator, of course, is that this is a close approximation of your error. And secondly, it should be computable in a cheap manner. That is crucial because at each iteration of your reduced basis algorithm, this error estimator needs to be evaluated multiple times. So for as many parameters you have in your sampling set. Therefore, it's crucial that it's computationally cheap to evaluate. That was a bit about the error estimators. Let's look at how you can also put the reduced basis method in this unified structure that I already mentioned. Once again, the setup is same as the POD. So we have this projection using the POD modes and then the unprojection using the V. And we have the latent space where the ODE is propagated. Now, the key difference in the reduced basis method is, of course, that this part is iterative. So in the latent space, when we solve the reduced order model, we also check the error. And if the error happens to be large, then we go back and we do the updates of the encoder that you have, which is the projection basis V. And in this way, you can ensure that your reconstruction is quite nice. Just a numerical illustration of the reduced basis method on the same Burgers equation. So once again, the setup is all the same as before. On the top right, I show the plot of the error, the estimated error delta mu over the number of iterations of the greedy algorithm. So you start at some large error, let's say close to 10 power minus 1. And as the number of iterations proceeds, it converges to the desired tolerance of 10 power minus 4. So this example took like 6 iterations to converge, meaning very importantly, we only had to solve 6 full order models. And that's a huge benefit when compared to the POD because we just randomly picked 50 parameter samples and then the error was still not as small as the reduced basis method. But here, for the reduced basis method with just 6 full order model solves, if you see the error in the test error, reconstruction error here, it's already 2 orders of magnitude smaller than what you can get with a vanilla POD approach. And also because we do the greedy sampling, the time taken is also less for the reduced basis method. And the inference times are, of course, similar. But just as a disclaimer, so I'm not implementing the standard reduced basis method in this example. I implement an adaptive version of this, which was developed together with my PhD supervisors a couple of years back. So this is a slightly more improved version of the reduced basis method that you can use, which really gives you tremendous speed up and also nice reconstruction error. That was a reduced basis method. Just to compare the different projection-based approaches so far. So POD and the POD hyperreduction are, you can call them easy and medium easy. But of course, the accuracy is not always quite good. But if you look at the reduced basis method, of course, the difficulty is quite high because you have to come up with nice error estimators. You have to implement the greedy loop in your code in an efficient manner. But the advantage, the payoff that you get for that is that you need less data, meaning you only solved 6 full order models in the example that I showed you. And you also get very nice accuracy for the number of solves that you actually make. Overall, it's, of course, a trade-off. If you want easy implementation, if you want an interpretable model, then, of course, POD or POD time might be good. But reduced basis method, while it's a little bit more involved, but it gives you nice results. I just wanted to also emphasize that the reduced basis method is not just for toy or benchmark problems. It's been used for more realistic applications over the years. For example, back in 2012, the group of Rea Manzoni looked at shape optimization using the reduced order model coming from the reduced basis method. Then people used it for 3D helical magnet surrogate modeling. I've used it a couple of years back, to model the dynamics of the left ventricle of the human heart. And also I used it in this very large scale example of the 3D dielectric filter here, which is almost a system of order, I think 400,000 if I'm not wrong. And we were able to get very nice reduction out of this. And also industry has picked up a reduced basis method. There's this company based in Switzerland called Axelos, who's one of the main methods that they use in their software is, of course, the reduced basis method. Then let me just briefly touch upon some data-driven methods. So far what we were speaking was that, we knew the PDE, we knew the models, we knew the matrices E, A, B, and so on. But what if you don't have that? So that really motivates the data-driven approaches. So what if we have only the data, the snapshot data U, but we don't know the model? So there are a huge variety, a zoo of methods that look at these data-driven setting. I want to first talk about the operator inference method, which is a very recent method developed in MIT. So the idea there is that, okay, if we don't have the model, let's just impose a model, whatever model that we want on the data. So for example, if you have data of the dynamical system, they impose like a quadratic model as shown here. And the main steps of the algorithm are also very simple. So you collect data, you apply your POD, obtain your projection basis, you do the projection step in order to get the reduced snapshot matrix. And because you have derivatives imposed in your model, you also need to compute derivatives of each of the columns of the reduced snapshot matrix. This can be done, for example, using automatic differentiation techniques, or as they do in this original paper, you can also just simply impose a finite element stencil in order to get the derivatives. And then the next one and the final step is, of course, to set up an optimization problem where the knowns are the following. So you know the derivative data, which you just computed. That's one of the knowns. And you have all these, the snapshot, the reduced snapshot, the quadratic version of the reduced snapshot, which you can just obtain by multiplying, and also the value S, which are just nothing but the inputs at different times, S at different times, T1, T2, and so on. So these are the knowns. And the unknowns you solve are these A hat, H hat, and B hat, which once you solve this linear least square optimization problem, you get as an output. And this allows you to, formulate the reduced order model using this reduced matrices and then solve the ordinary differential equation. The key step in operator inference is, of course, you need to regularize. Without regularization, you usually do not get good results. Some more details about operator inference. I just showed a quadratic model here, but people have also looked at higher order polynomials. There is also techniques to look at more general nonlinear systems by consider what are called McCormick relaxation or lifting, where you kind of come up with embeddings to make the system quadratic. I guess a couple of talks back in this seminar series, we also saw a talk that is related to quadratic embeddings. And operator inference has been combined with hyperreduction and also active learning in the literature to make it more efficient. Just to summarize the plus and the minuses. So the plus is, of course, that you don't need the model anymore, and the results are interpretable because you are imposing the model yourself. The drawbacks are, of course, similar to what the POD-ROM suffers from, which is need for large amount of data, and also the regularization is quite important in this approach. Operator inference has also been applied to very large-scale systems. For example, this very recent paper from earlier this year, where they looked at this detonation engine coming from one of the US Air Force applications, where the number of dimension was 4 millions, and then they reduced it to something as small as 12, which is the result you see here on the screen. So you can also apply this to very, very large-scale systems with fairly good results. And in the unified structure, the operator inference, once again, very similar to the POD, but once again, like I mentioned for the previous example in the latent space, instead of directly solving the reduced order model, you learn the operators of the reduced order model, the A hat, B hat, and so on, and then you propagate the result into the latent space. So you can also put the operator inference in this framework. Quick look at another closely related reduced order model approach, which is the POD-NN. So this can be thought of as an upgrade of the operator inference in the sense that you have the first two steps to be the same, but the key difference arises in the third step. So in the operator inference, we learned some matrices, which gives you the reduced order model. But here in the case of the POD-NN approach, which was introduced in 2018, we learn instead a map that takes the time and the parameter directly to the reduced POD coefficients U hat, which are basically the columns of this matrix. And then if you want to query the model, you just apply it a different T and the mu, and then you compute the U hat. Once again, the advantages are similar to operator inference. You don't need to know the model, and the implementation is easy. Because you have to learn this map using some kind of a neural network, you need to look at hyperparameter optimization as well as a critical factor. In the unified structure, this is how POD-NN looks. So the NN stands for neural network, and that's where the feed-forward neural network comes in. So we have the same POD-based encoding and decoding paths, but now we also have this additional hyper network, which learns the mapping from the time and the parameter to the reduced coefficients. So in the online stage, we just use this path. So we map a U hat and then use the decoder to obtain a reconstruction. So just to give you a glimpse of how this works in one of the examples from the original paper in 2019, they considered a 1,000-dimension system, and the kind of speed up that they expected is quite high. So this is like 6 orders of magnitude improvement. So 10 power 3 seconds to solve the full order model, and also 10 power minus 3 to solve the reduced order model. And the training time, of course, is quite large because the feed-forward network has many parameters to learn. But nevertheless, you get very nice speedups. So this is the DL-ROM, the deep learning based reduced order model, which was introduced just a few years back in 2021. Once again, all these approaches are very, very similar with just slight differences between each other. So instead of a POD, the people who introduced DL-ROM, considered a convolutional autoencoder. So you don't have the V transpose V mapping, but instead you actually have convolutional neural network doing the encoding and also the decoding. And you also have this second network, which learns the mapping from the time and the mu to the reduced coefficients, or in this case, the encoded representation. And this is how it looks. So instead of the V transpose and the V, we have this convolutional encoder and the decoder, and the setup at the top remains the same. And the idea here is that the loss function has two components. So you try to minimize the reconstruction loss from the autoencoder in the first part of the loss, which is U minus U tilde. And of course, the second component has to do with the convergence of U hat towards U hat FFN. So they want to somehow push U hat and U hat FFN to be the same, as close as possible, so that these both approximations agree in some sense. So that's the idea of the DL-ROM. The DL-ROM is quite good, at least when it was introduced, but the major issue that it had was it took a lot of training time. So they applied this in the original paper on a 16,000 dimension cardiac mechanics model, but the training time really killed it. It's like several days of training, and this was not really paying off. So what they came up instead was this slightly improved architecture, which kind of fuses two things. In addition to the encoder and the decoder, they also have a POD projection step before and after the encoder and decoder respectively. So now what you optimize for is, of course, this reduced state to be the same, which is this part of the loss function. But instead of the full state U and U tilde, what they did was to reconstruct the projected versions of U and U tilde. So V transpose U and V transpose U going into the encoder part here. So this somehow reduces the number of parameters that you have in the convolutional autoencoder network. And that's how they also illustrated this in one of the examples, where they applied this on the Navier-Stokes equation 2D. And they say that, if I apply the DL-ROM to this, it took like 58 hours of training. Whereas if I do this extra POD step before the DL-ROM, then they were able to show that you just need 58 minutes of training to get this. And this is how the reconstruction looks. On the left is the true solution, and on the right is the approximations. That's a summary of some of the deep learning based methods. Of course, there are a lot more methods to talk about, but that's not enough for one talk. So I just want to summarize briefly by saying the following. Reduced order modeling has a long history in engineering and mathematics. It's not new. It's been around since the 70s and the 80s, and continues to be a very active topic of interest in both in academics, and also I think it's been increasingly adopted in industry. Projection-based methods are great when you already have your base model or the underlying full order model known. Then it's very easy to do the training, and also for the linear reduced order model, maybe the inference cost is a little bit high, but there are methods that address this as well. In terms of data-driven or ML-based approaches, they are best when you don't have any idea of the model, all you have is data. So then you can just directly fit your neural network to learn this model. Of course, the training costs are quite high, but as we saw, there are many works trying to reduce the training cost. But once you train the model successfully, then the inference is blazing fast. Like I mentioned, there are many other methods of reduced order modeling, which I did not talk about, such as nonlinear reduced order models, frequency domain methods, neural ODE spins, but that's for some other day probably. With that, I would like to thank you for your attention. Thank you.